So having more views of this exact same sketch, or not the exact same sketch, but the same object being represented, gives us more information about the design that we're trying to build. So this would be our first layer. Um, Essentially, it's a top-down view of nothing but the drivetrain and the basic shape of the chassis for the robot that we're going to build. Moving on from that, though, we actually have to include um, some more details, or we have to start appreciating the fact that this is supposed to be a three-dimensional object. And to do that, you add other angles. So if this is our top view, then below it we can draw either a front or a back view. And using the graph paper that we have, we can make sure everything gets lined up properly. So to do this, I'm going to come down probably six graph squares, and I'm just going to make a dot. I guess that's only five because I can't count. There we go. And I've made a dot right here. I'm going to zoom in on this a little bit more. I forgot that was something that I've had to do. Come on, keyboard. There we go. I think I need to replace the batteries in this thing. And stretch it out. There we go. That's good enough. Okay. So it's still hard to see the dot that I made, but it is right here. And it is in line with one of the vertical grids from the top part of my chassis. And coming straight over to the other side, which I believe was 18 squares if you're counting them, but you can also use the end of the shape above. I have made another dot, and then I'm going to connect them. And this is going to be the top line of the chassis. There we go. That we drew ahead, above, but this is going to be, like I said, this is going to be a front view of this chassis, or I guess the back view works too. It doesn't really make a much difference. It doesn't really make much difference because this is a very symmetrical design. So, because remember we're using inch material, so inch by inch material to make this. Then we're going to come down one square and draw across going the other direction, or the same direction, I guess. There we go. Now we need to make sure we represent the different pieces up here. So I'm going to draw this line and this line here, and make sure that you're, and sorry if I wasn't obvious, you do need to be following along with your in your sketch with this. So we came down here and here to represent the front end of this piece and the front end of this piece. Now, we do have the wheels on our view up here, but we don't want to draw them in yet because in actuality, these wouldn't be sitting flush or wouldn't be sitting on the same plane as this part of the frame. They would either be below it or above it or um, someplace, there you go, more near than that. So let's take a look at how that works. Give me just 1 second. There we go. Okay, good. All right. So, in order to make this chassis three-dimensional, we need to think about how it would be supported and how it would be put together. So one of the things that we have mentioned but haven't actually talked about in terms of designing with is what actually powers our wheels. Right now, if we were to build this chassis the way it is exactly, then our wheels would be they would all be unpowered because they don't have any type of transmission attached to them. A transmission that we would attach would be a specific size, and we're actually going to use a very specific transmission for this one called a Tough Box Nano. And let me pull that up so you can see what a Tough Box Nano is. I know you can't see my screen yet. Do, 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 do. Ooh, somebody made one out of acrylic. That's kind of cool. Nope, that's just the connection hardware. Do, 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 do. Um, Hopefully this one takes me to the right place. Okay, so these are they're a product that has been discontinued by the company that we would buy them from, but they are the most they're the easiest ones to use when you're doing a sketch drawing, and we also have a ridiculous number of them on hand here at the school. But essentially, it's an inch wide, it's 4 inches long, and it's 2.5 inches tall. Um, or no, I take that back. It's 3 inches tall and 5 inches long. So it's 1 by 3 by 5. There we go. And it looks like, and if you want a visible representation, this is what they look like on the inside. So you have the big gear that is driven by these two sets of interlocking gears. There's two of them to help provide more torque and more, or not torque, but more connecting power between the intermediate gears and the actual driving gears. And then there is the sim, which is this motor here, and it's attached to a much smaller gear that drives the whole thing. So this is actually a really cool representation of this that I'm going to have to keep because that's the first time I've found that. There we go. So anyway, this is basically what we need to include in our design. So if we say, or if we know that this height is 3 inches, then we need to account for that in the design of our view. Now, the first thing that I want to do is figure out where I want to place it. And generally, transmissions are connected on this inner section right here. Simply because if you put them on the outside, then the motor and the sensitive electronic connections to the motor can get ripped off by the robots. So you want to kind of keep them protected by putting it towards the inside. So that's what we're going to do. We're going to add to the sketch on top. Uh, so essentially they're called hidden lines, but we're going to do it in such a way that we don't need to change pencils or colors, which is what you would traditionally do if you were actually using proper drafting techniques. But we're just sketching at the moment, so this is going to be fine for this. So I don't have this written down anywhere, but I do remember these specs. So if we look at this top view here, we're going to make it so, remember I said it was 5 inches long. We're going to start here because it's 1.5 inches from the front edge of the tough box to the center of the gear. We placed our wheels so that they were 3.5 inches. 2.5 inches rather. No. Yes, so we made it so that our axle was 3 inches away from the front edge and the back edge of our chassis. So 1.5 inches means that we're going to come here, and about halfway through the second box back, we're going to put a couple of dashed lines. Now I'm going to zoom in on this again because this is still hard to see. It'd be nice if I could just zoom without doing this stretch thing, but it doesn't like it when I play with the camera zooms. Okay, so right here, I just put two little dashed lines to represent the front edge of our tough box while it's been hidden. And it's being hidden beneath this top piece of metal. From there, I'm going to come back to the center of the next box, and that's 1. Center of the next one after that is 2, 3, 4, and 5. Okay. So now I have these dashed lines that are 5 boxes apart, and they're running through the center, or like the halfway point of the boxes that they're in. And I'm going to do that for all 4 wheels, because this is going to be a 4-wheel tank drive. 1, 2, 3, 4, 5. Once I have one done on each side, I don't really need to worry about counting on the other side. I just have to transfer those lines across to find them on the other side. Now I am going to go ahead and add the sims to these. The sims are going to be 3 inches long, sticking off the back side of our transmission, and they're about 2.5 inches in diameter. So I'm going to represent that by doing this. So 3 inches, 2.5 inches down, and then I'm going to lightly shade that in. And I'm going to do the same thing for the other ones. There we go. Alright, so that gives us some power to our chassis top. So now that we would be able to move it as long as everything was hooked up properly. Okay, so why did we have to do this before we finished our front view? Well, we had to because we needed to know we need to make that decision before we knew how tall our robot was actually going to be. So let's take a look here on this view, and one thing I didn't do was put in hidden lines that represent where this connecting piece is on both sides. So that's what I'm drawing in right now, just by drawing those same style of dashed lines like we did up here for the tough box. And then below that, it'll be a solid 3-inch rectangle. And this represents the front view of our tough box. Now we don't have to do any other hidden lines, even though 2 of them are hidden behind this. And the reason for that is because they are, well, they're perfectly in line, so you wouldn't be able to see them even if you did put hidden lines in. And then I'm going to put my sim in on both sides and shade them in. So remember, 2.5 boxes by 3 boxes. There we go. And then on the other side, we're going to have a 3-inch piece of the same metal that we're using for the frame. It's going to look exactly like your sketch for the tough box, but which is just a rectangle that's 3 cubes by 1, or 3 squares by 1. And then we're going to box the bottom in with the exact same type of thing that we did at the top. So it's going to be a rectangle that covers the whole length, hidden lines that represent the same type of supporting structure along the bottom, and then solid lines that represent the front end of another layer of this exact same chassis part. Now, the only thing we have left to do is put our wheels in, and some of you may have noticed the issue that we would come up with this type of robot using the size wheels that we chose. And that issue is that if I put a wheel in that's 4 inches centered here, then the wheels aren't actually going to stick out of the bottom of my robot. And the reason for that is because we have a robot that's 5 inches tall, and we have wheels that are 4 inches in diameter. So what would we have to do to change that? Well, we would need to switch out to probably 6-inch diameter wheels. And we could definitely do that, and that's actually what I want us to do. But you're going to notice one thing when you start to sketch this out. If you change these to be 6-inch diameters, it looks like they're going to touch the front frame of the robot right here, and the same at the back. And if the front was a solid piece of metal, that would be true. However, there is actually, so this is actually an open space here. So that front curve of the wheel won't actually be touching any metal, but it will allow us to successfully touch the floor through the frame of our robot. Okay. And I'm going to go ahead and finish putting those stripes in that I didn't do last time. You may notice, I think last time when we were in here, I was using one of my actual drafting pencils while we did this. Or maybe I switched over to this before the end. But the reason I'm using this specifically instead of an actual mechanical pencil, which is better for sketching of this nature, is because it's much harder to see the lead that's in my mechanical pencil than it is to see this B3 pencil. Alright, so if we have 6-inch diameter wheels, and they are centered on the middle point of this gap, so if we come up 1, 2, 3, then we have our wheel sticking a half of an inch or a half of a box out the top and out the bottom. Okay. And then I'm going to put some marks to represent the parts of the wheel are hidden behind the front frame. And then I'm going to put my diagonal lines through it that are helping identify that this is a wheel. I'll go ahead and make them go through the hidden line portion too, it's fine. There we go. So same on the other side. And then realistically, there would be some collars and stuff like that in here. But on a sketch, we don't really have to put anything in except something to denote our axle, um, so that our wheels, there we go, have something to actually be resting on. Alright, so with that, we went from having a flat, definite, or a flat drawing that we know we were intending to be the chassis of a robot, but it didn't really have any of the defining features so that if you handed it to somebody else, they could go, hey, this is a robot chassis. But now, we've put the rest of our identifying features on for the wheels. We've added some transmissions to them, which you might still have to explain what they are. But it's obvious that these are a different representation than probably the metal frame. The only thing that we don't really have anything specified for is the tough boxes over here, and there isn't really an easy way to do that because we're starting to get kind of cluttered. I mean, so really, if you were describing this to somebody else, you would just have to, excuse me, you just have to tell them what those are. The other thing that you could do is if you have different colored pencils, you could denote different objects by using different colors. You would need to keep some sort of a legend on the paper, though, so that other people would be able to identify what it was that you were talking about. So, ordinarily, we would also have a side view in place, but actually, I think this is pretty good for this one right here. But so for this particular design, I did basically give you all of the specifications for it. Uh, but depending on what your challenge is, you have to think about the different ways that designs can happen. We had started off by talking about having a robot chassis that could you would have, or you made up what it was, and it should have been able to drive over carpet or slick surfaces successfully. Um, but when I gave you that idea, we hadn't really talked about how you actually go about designing something. And now that I've given you an example of what a design should be, you would probably be a little better able to come up with some sort of drawing to visually represent what it is that or what that you're trying to get across. Um, However, we want to take a look at other designs. So there's chassis design, and then there's other components that have to go into creating a robot. Just getting around doesn't necessarily solve the problem. So let's take a look at this video. It's about 7 minutes long. Um, and we will reconvene after the video. So let me remember how to do this. I want to share screen, and I want it to be this screen. Share the computer sound. And there should be sound. All right. Could you guys hear that? Okay.
Hi there, my name is Grant Imahara, and I'm one of the hosts of Discovery Channel's Mythbusters. I'm also an electrical engineer, a robot builder, and, oh yes, a former FIRST mentor. I'm here to talk to you today about the importance of design. Look, I know what the first season's like. It's intense. Everyone wants more time, right? Well, you don't get more time. No, no, you don't. But through design, you can make better use of the time that you have to be more efficient and get more done. Now, I know it's tempting to just grab a piece of aluminum and start building the first thing that pops in your head. I know, I have. But this really only works for very simple challenges. And as we all know, FIRST is anything but simple. FIRST robots are, by nature, complex machines. In order to build them with the capabilities that you want, given the time that you have, requires careful thinking. The design process is your roadmap through this minefield. Seeing that journey and understanding the process of design is what this video is all about. Now you're saying, I already know all this, Grant. What's the difference? Well, the difference I'm suggesting is that you pay a little more attention to the very early stages of your design process. Now you're probably thinking, whoa, 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 we do design. We draw it on a piece of paper or on a whiteboard and then we build it. Well, before charging forward to making parts, just take a little time to make a study model. It can be in the computer using CAD, computer-aided design, or it can be popsicle sticks and paper towel tubes. It doesn't matter what you use, as long as it helps you work out the problems. Because, let's face it, making a part over and over and over again is not only frustrating, but also very time-consuming. You know what I mean. You make a part, you test it, you take the assembly apart, put it on the drill press, drill a new hole just a little bit further, put it back together, rinse and repeat. In the end, you've got something that looks like a piece of Swiss cheese rather than a robot part. By using a model to test your ideas before making parts, you'll save materials and time. What? You don't believe me? It's already been done by many teams. I'll show you. Within FIRST, there are hundreds of instances of great design, but today we're going to focus on one notable example of Wildstang and their lifting arm. This is their design story. Step 1, define. Understanding the problem. The challenge was to single an inner tube from the floor and lift it up 8 feet using a mechanism that was limited to an initial height of only 5 feet. The design needed to be strong, lightweight, and controllable. These requirements and constraints define the problem they're going to solve. Each part of the design stage is a jump called a kinematic analysis. Basically, how small did the robot have to be to begin with, how long the arm had to extend, and the types of movements required. They used hand sketches to quickly identify the critical dimensions. Based on this analysis, they established that 2 linkages connected by rotational joints could accomplish this task. Step 2, ideate. Brainstorming. As a result of their discussions and brainstorming sessions, the team decided to model their robot arm on a human arm. The robot arm would rotate along 2 axes at its shoulder and along a single axis at its elbow. They decided to make each aspect of the arm analogous to a human's, with linkages as bones and power sources as muscles. Next, they had to build what they imagined. Step 3, create. Building. Team Wildstang used the CAD approach, building their arm in the virtual sense, in the computer. But as I mentioned, you can use whatever you want to make your models. They divided the arm into its major components, the shoulder, the upper arm, and the forearm/gripping system, and assigned each part to a different subteam. These subteams worked independently to model their designs using CAD, and then put all the models together for testing. Early testing revealed that the original gripping system could hold a tube, which is good, but the tube rotated if you moved the arm too quickly, which is bad. Within the computer, they then easily moved around the pivot points until the arm had better range of motion and a stronger grip. The whole time they kept plugging away at the models to improve performance. See, they did all their testing in CAD and solved the problem virtually before any of the parts were actually made. Their computer corrections solved the real-world problems. Now that their virtual design was working great in the computer, it was time to make the parts and put the robot together. Step 4, solve. Manufacturing. Wildstang's CAD models not only helped them test the arm, but also served as detailed blueprints for fabricating the actual arm components. Each bearing, mounting hole, and attached part was precisely specified in the CAD model. This allowed them to make the final parts in one pass, saving materials, and more importantly, saving time. The result? Wildstang's arm had a full range of motion, was easy to control, and was strong. A phenomenal success. They used CAD to streamline their design process to keep them moving forward toward their goal. To review, make a model, work out your ideas, then make your parts. And like Team Wildstang, you can follow the same design path to efficiently create an elegant solution. And that, my friends, is what great design is all about. Or you can struggle through it the hard way. It's up to you. Either way, you better get started. Clock's ticking.
All right. Um, what they were talking, or so one of the main things they were talking about there is the design process. There are a bunch of different names for this, uh, or a bunch of different. There's sometimes some different order of operations and different situations where you'll add other steps. But the engineering design process, which is the full name for it, basically revolves around those same 5 to 6 steps. Ask what is your problem, fully define it. Plan what it is that you want to do, accomplish. Improve that plan. So go through and take what your ideas are, reevaluate them, come to a consensus on what the best solution is. Excuse me. Actually create the solution that you've come up with, and then communicate or go back to the drawing board. Sometimes this is called the design cycle. Some of them get very, very complicated. So, I mean, this is probably one of the more complicated visualizations that you'll see, but it does do a very good job of saying or of pointing out which each one is. So, explain and justify the need, identify and prioritize research, analyze existing products, and develop a design brief. We've kind of done this part a little bit out of order in the beginning. So I gave you a problem to solve. I didn't really explain or justify the need for the solution, other than it was an assignment to do. Um, and then I wanted to see what you would come up with on your own, so we hadn't really done the research portion of it. I also didn't have you analyze existing designs or products, but we did develop a design brief or a sketch. So now, if I went back to the beginning and gave you that same set of steps again, you could probably come up with a much more complex solution than you did the first time around. The next step up would be to develop your ideas. So develop design ideas, develop design specifications, present or justify the design. Here we go. Let's do that. That's better. Um, and then develop planning sketches. So we're kind of in this area right now, except that I have been giving you the design fully. So the next step from that would be to construct a logical plan. Demonstrate technical logical skills, follow the plan to create a solution, and justify any changes made to the plan. And then test and evaluate. So at that point, you would start actually building something, or we could put everything together in CAD and test it virtually before we ever put any pieces of metal together in the first place. We are somewhat limited by our situation this semester. It is my intention to work through several of the design. Basically, we're going to focus on the design more than anything this semester. And to do that, We're going to draw, like I've said before, very heavily from several of the first challenges. So, that being said, we have now sketched a chassis for a robot, and we have looked at the different ways, different materials that go into making the frame and drivetrain for a robot. Now, I think I'm going to go ahead and introduce to you the beginning sections, or the beginning challenge that we're going to work on as a whole. So, before we do that, I want you to turn in your notebook. So we have the first page, which is going to be your table of content. We have the second page, which is where we've done our preliminary sketch. I want you to turn 3 pages further forward. So you have 3 blank pages, and then this is going to be so we can add some more sketch work in later. This is where we're going to start working on our first actual robot challenge. Now, one of the things that I'm going to put together is, let's see how many of you. There's 10 people in here. Let's do. I'm going to group you off into groups of 5 for this, and it's going to be randomly chosen by Canvas, or at least I think that's how that works. Here, just a second. Come into here. Where is what is Brain Pop? That's new. Actually, I think I had this question last time. Okay. All right, groups. There we go. And I'm going to set a new group. And a split into 2 groups evenly. Oh, right. Do, 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 do. There. Alright, so it will randomly assign you guys to your group, and while that's happening, I want to find our design challenge. Challenge 2015, I think, was the one I wanted to use for this. Archive game documentation. Probably should have had this downloaded. Actually, let's do Rover Ruckus. That was a good one. We can do Relic Recovery later. So, download manual part 1, download manual part 2, come back into Canvas. Alright, so you should be able to see your. Remember how to view that section. Let's see here. If I remember right, down the side of your screen you have groups over here, I believe. Is that correct? I think if you click on that, you should be able to see the groups that you are in. And I don't know why that is. If I click people, oh, maybe that's it. There we go. Actually, so if you click on people and then click on groups, you should be able to see which group that you are in. It has automatically assigned you to each group. And the way that we're going to go about doing this is I'm going to set up let me get out of student view here. I'm going to set up a discussion, and you guys can collaborate inside of your discussions. Let's see here, create a discussion. I want to post to the whole class. This is going to be graded. Threaded replies are fine. This is group discussion. Challenge group A. No, I don't want to. No, I don't want to create a new group. There we go. It's going to be worth 15 points. It's going to be in a classwork group. be due on Sunday night, basically. Alright, so essentially what I'm going to do is create a thread for each section, essentially. So ROBOTCHLNG, each group needs to look through the manual. That is, there you go. Posted below and utilize the restrictions presented to meet the challenge described. DSCRIB. Alright, file. I want to upload a new file. I want to choose a file. I'm going to go to my downloads, and where did those get saved? Oh, it hasn't actually downloaded them yet. Yes, it did. Where'd it go? Show in folder. For some reason, we're downloading directly to my desktop these days. Choose file, desktop, part 2. There are 2 parts to each FTC manual. You don't really need part 1 because it just describes different non-game specific information. So everything you'll need is in part 2. This is a pretty lengthy manual, but you can find it, and we're going to flip through it here in just a minute. Each group leader will need to create a reply to this, and then each group will reply to that reply in creating a thread. What you're going to do is come up with different sketch designs to meet. So each person in the group is going to come up with different sketch designs to meet the challenge presented in the manual. For that particular game, and we'll watch the game animation for it in just a minute. And then through the group discussion, and I have it set to be finished on October 4th, but actually let's make that longer. Let's make it until the end of the day next Friday. That gives us quite a while to come up with ideas and decide which ones you guys think that you want to go with. So GRO leader is to see THRD, and the rest of the group will ESPOND to the first post. Alright, so let me go ahead and assign this so that you can see it. Save and publish. There we go. Since this is a group discussion, each group has its own conversation topic. Oh, perfect. Perfect. So, yeah, there we go. Alright. So, you should be able to see... Actually, that should be turned off. I need to turn that on. Settings, and sections, and navigation, and discussions need to be turned on. That can be hidden. Good. Save. Alright, so if you refresh your Canvas page now, you should see discussions as an option, and inside of there, you'll see the discussion robot challenge that you guys can respond to. So let's take a look at the game animation that goes along with the assigned challenge that we're going to do. So 2018 Alright, this one I believe is no intro. There we go. We don't get to see the cringy acting. Okay, that's weird. All right, so we'll watch part this to start with, and then we'll start looking at the manual real quick. Share screen, share computer audio, and So, one of the things that I have done, and you guys should be getting an email about this shortly, and if you did not, then the really irritating issue where your email addresses are backwards from the way they originally were has struck again. But I've created a couple of Google chat rooms for you that you can use to talk more quickly than using the discussion board on Canvas. So I'm actually going to remove that, including the. Let's see here. I'm just going to delete it. There we go. Uh, we'll use discussion boards for some things later, but it's really much faster if we utilize this. So, yeah. Good. So, what you're going to do is we're going to start off, and I want you guys to look through this manual. It's only 35 pages long, which is a lot, but at the same place, it's not insanely long as the 180 some page game manual for the first robotics challenges. But it goes through and details the information about. Let me stop sharing. There we go. It details information about the game field, how it's set up. What you're really concerned with at this point is creating a robot that meets the information given to you in the robot rules section, which starts in where is it? It should be R. Starting on page. Come on. I think starting on page 16. So it'll be under the rules of gameplay. But it'll go through and give you specific information about the size of the robot, what parts can be used, and different ways that you can meet the challenge. Now, specifically, what you're looking to do right now and is design and settle as a group on what type of chassis that you guys would like to use to create this robot and what kind of wheels and what kind of drive system. After you, as a group, decide what you would like to use for this, then we will go on. And I'm not going to stop you from starting to brainstorm different ways to actually create the mechanism or different ways to solve the challenge using a mechanism, but we're going to talk more about designing arms and scoopers and grabbers and things of that nature, probably starting on Friday. But I'm going to give you guys and your group the rest of this class period's time to start brainstorming. I am in the chat with you guys, so if you have any questions, I think you can at people inside of Google Chat. It's been a while since I've used this as more than a quick way to keep in touch with a couple of my friends. So it's been a while since I've used it as a group. But cool. So, go ahead and start looking through the manual, start asking questions, start coming up with designs. Definitely divvy up tasks. I would recommend that you all come up with some preliminary designs separately, and then as a group decide which ones you would like to actually utilize. Remember, this can be you have to decide on drivetrain, different types of not transmissions, but different types of movement situations, wheels, materials, things of that nature. And you can find specifics about what is actually allowed inside of the manual. Um, all right. If you guys have any questions, be sure to email me. And one thing. Sorry, I meant to include this earlier because I've been including it in all of my classes. But generally, my homework assignments are due at midnight on Sunday nights, which just gives you the whole weekend to work on stuff. It actually gives you from the time it's assigned until then to finish it. The difficult problem is when you guys decide to start working on homework at 9:30, 10 o'clock on Sunday nights, and then you have questions, and I'm old. Usually by about 9:30 I'm either in bed or already asleep on a Sunday night, and that's really not a good time to be asking questions and expecting responses. Generally, through the whole weekend, I do answer emails as soon as I get them or as soon as I notice that I have gotten them. However, yeah, Sunday nights are not really a great time to be asking questions. So, I would recommend that you make sure you check through your assignments before then and make sure you don't have any questions, even if you do decide to wait until last minute to complete them. But so I'm gonna go ahead and, like I said, give you the rest of the class time to look through the manual, start asking questions, coming up with or come up with design ideas for each other or with each other. The other thing that I would heavily recommend that you do is check Canvas, the grade book in there to see what you're missing. I have not pushed this class's grades over to Skyward yet this week because if I were to do so at this point, most of you would not be doing so well. So please get anything that you're missing turned in to me. You should be able to see what has been due in the Canvas calendar, um, and you should also be able to see a list of what is missing for you in your to-do section. Um, yeah, so which I think at this point is basically wheels and drive trains chassis is the only thing that has really been turned in so far, and I'm missing from most of you. So if you have any questions, comments, or concerns, email me. I'll answer, or you can put it in your group chat. And if it's not you specific, and we will see you on Thursday then. You guys have a good one, and have fun.